All right. I'm hoping that this is going to be the very, very last video, so you'll be listening to my voice just a little bit longer, and then we'll be done. All right, video number 4. All right, now this is the stuff that we just dealt with, so this should be the freshest in your brain. So let's go through it. All right, the degree of vertex E. E is being connected 5 different times. Is this an example of a connected graph? Yes. Everything is connected one way, shape, or form. But if you notice, this is a complete graph as well because every single vertex is touching every other vertex, meaning A is touching all of the other vertices. B is touching all the other vertices, so on and so forth. So that would be a complete graph. Now, what is the chromatic number? A lot of folks struggled on this. Now, if I was going to label A yellow, nothing else can be yellow because they're directly touching it. So that means E would have to be a different color. Notice E is green, nothing else, because E is touching everything else, meaning all the other vertices. B would have to be blue, but B is touching everything, so it can't be the color. And then purple, I'm kind of running out of colors here. So F would be purple, same thing. Everybody is touching everybody else, so there cannot be any shared labels. So if this was the red vertex, nothing can be red. And if this was, we already did purple. C, the blue vertex, again, nothing else can be blue. So the chromatic number is 6. The following graph represents the city, various tourists. Now remember, we're looking at basically a map. The way to get to your house is through here. No, let me try this again. And I don't even like that color. So you go house, go through B, go to C, then you go up to F, G, and then Huddle House. There you go. That's the quickest way to get from your house to Huddle House. The following graph represents streets and miles. All right, so does this have an Euler circuit or path? All right, so Euler circuit or path. Remember, Euler means everything. Everything has to be done. Now, you can guess and check this, or if you can just go by the degrees. J has degree of 2, D has degree of 1, 2, 3, 4, H has 2, F has 3. Oh, F is 3. That means it's automatically not going to be a circuit. A has 4, G has 1, 2, 3, 4, C has 3, L has 1, 2, 3, 4, M has 3. Oh, that's my third odd vertex. It will not be a path. That is going to be a neither. All right, create a graph from the adjacency matrix. Remember, a graph means straight lines. There you go. Remember, you do not repeat. Do not repeat edges. Do not repeat edges. All right, let me put an exclamation point on there just to show you how serious I am. All right. EST. Now, it says, at the beginning of the week, Chris supervisor had many jobs for his crew to do. So we've got to figure out from start to finish, how many hours is quick, or the quickest. All right, so EST. Start is going to A, 0, 0, 0. Now, look at D here. There's 2 arrows going to D. A will get there faster, but D cannot start until both of them get there. So that means although A will get there at the 2-minute mark, B will get there at the 3-minute mark. So that means A is going to be sitting around for a minute before, I guess this is hours, for an hour before B gets there. Now, A is the only thing leading to E, so that means E will start at the 2-hour mark. A and C, notice they're both going to F. A will get there faster in 3 hours. But notice that C is the longer one. C will get there in 5 hours, and you're always taking the longer. Looking at G, same thing, 3 and 2. E will get there in a total of 8 hours. D will get there in a total of 11 hours. D wins. All right. Next is E and F. E and F, let's see, E will get there in a total of 8 hours. H will get there in a total of 17 hours. Nope, 17's it. And then 11, let's see, H to finish, that will be 18 hours. But G obviously is a very long task. That will be a total of 31. So 31 is your quickest time possible. Now, so what a lot of folks think is quickest time is like the fastest you can get to. Like a lot of mistakes was A all the way to here to here. They're thinking it was like that. It's not this, guys. It is not the early, because tasks have to start and finish at the in the correct order. So that's where the prerequisite task comes into play. So how do I do the critical path? Well, just figure out how you got all these numbers. D became 3 through B, A became 2 through E became 2 through A, C became 5 through F. Let's see, H is 17, that came through F. D is 11, that came through G, and lastly, there we go. So start, B, D, G, finish. There we go. Remember, the arrow is pointing to the loser. So the one that has the most arrows is the loser. Notice that D had 3 arrows going to it. A has 3 arrows leaving it. That's how you figure out the winner. All right. Does this have a Hamiltonian circuit? This is a Hamiltonian circuit means, can I connect the dots? And no, I don't have to touch every edge, but every dot has to be touched. And this is just one of several ways that I found to connect the dots. And I was able to get back to my starting point. There we go. Complete K5 graph. Notice that every single vertex is touching each other. So there was 10 lines that made this. Each vertex has a total of 5 degrees. 5 degrees, 5 degrees, 5 degrees, grand total of 20 total degrees. Create a diagraph. Remember, the arrow is going to the next person. N degree of D is 2 because there's 2 arrows going to it. Is the following a tree? Yes. This is not a connection point. That means we just have a twisted tree here. That's like if you take your arms and cross them. Just because you cross your arms does not mean they're connected at the elbow. So this is an open tree, which means, yes, it is a tree. Now, a Hamiltonian path means, can you connect the dots? Well, watch this. A lot of folks said yes on this one. Notice, it's all good so far. Oh, now I'm at C. I cannot go back to B. Can't do that. So that means there's no way I can get connecting C to G or B to C. Can't do that. So that is a big fat no, which means there is no Hamiltonian path. Starting breadth first. Remember, starting with 0. Anything that is connected to a 0 has to be a 1. There's a lot of folks that did not want to make this connected to 0 for some odd reason. There's clearly an edge there. All right, so everything connected to a 0 is a 1, and anything connected to a 1 is a 2. Now, if you remember that this 2 is connected to, let me redo this. I don't know what just happened there. Let's try that one more time. This 2 is connected to this 1. So you could have connected this 2 through this 1, but you had to make sure that it's like this. I don't know why it's messing up, but I won't ever do that one again. Remember, you're creating a tree. Do not create a cycle. Everything has to be open. Okay. Using Kruskell's minimal algorithm, I started with 5. So let's see if I can erase this, see if it works. So far, so good. I don't think anything was erased that shouldn't have been erased. All right. So starting with the smallest number. Smallest number is 5. Hey, there's another 5. After 5 is 6. There's a 6. Any more 6s? No. Hey, there's a 7. There's 2 of them. I'm going to do both of them. Well, I can't do this 8. That's a cycle. Can't do that 8. That closes in. So that means I move to 9. There we go. We're all done. All right. Creating a Hamiltonian, creating a Hamiltonian, I'm sorry, I don't know where I keep on doing. Starts, wow, I'm really struggling here. Traveling salesman, that's what it was. Wow, there it is, traveling salesman. I kind of blanked on that one. All right, so traveling salesman, these are all the routes that you could go. Notice that if you're doing a good job, everything is going to be repeated. There we go, 75, 75, 72, 72, so on and so forth. All right, let's view. Let me dual screen this thing. All right, so let's answer some questions. What is the weight of the shortest circuit? Well, weight of the shortest circuit was 72 because it was the smallest number. What is the weight of the nearest neighbor? Well, go back into your graph. Let's see. Home, nearest neighbor is C. From C, my nearest neighbor is D. My nearest neighbor technically is home, but I've already been home. I have to go to B. which is right there. And then from B, I'm going to complete my circuit. Boom, 72. If you were driving a car that fuel consumption of 25 miles per gallon and gas was 315, let's see, 75 is my longest route. I divide that by 3. I get a number and I times that by 315, sorry. All right, now a complement is all the missing pieces to a particular graph to make it complete. So here we go. Let's see, in order to make it complete, everything has to touch each other. So that has to touch that. Let's see, it's touching everything else. That has to touch that. That has to touch that. It's already touching that. Let's see, that has to touch that. That has to touch that. And that has to touch that. So everything that is blue is my complement. So I'm just going to take all of this and just convert it over there. There you go. Now I'm going to go ahead and stop it. We're going to do video number 5 to do the new stuff. And so thank you for watching.